So my lecture was about Lagrangian topology. So this is a subject that comes from celestial mechanics. Its origins are in maybe Kepler's n-body problem. And there are a number of very interesting rigidity phenomena in the subject, and then there are some flexible aspects. And my talk was about how this rigidity fits with flexibility. And an example of rigidity is how many periodic orbits a mechanical system can have, if it has to have many or few. And the most typical origin of these questions comes from the movements in the solar system and whether the movement of the solar system is stable or not, and if there are some stable points. And so this is sort of a modern topic, but inspired by this very old subject. So it's a subject that, as I said, comes from a very classical problem in the mechanics of the solar system. But now it fits very well with topology and differential geometry. And it's also related to various other fields like analysis and PDEs and complex analysis. And it uses techniques that come from all these other directions. And it started to produce also applications in some other fields, in particular dynamical systems and others. Well, it's I mean, I was very interested in astronomy when I was a kid, when I was like 6 and 7, and then later on I discovered that I'm more interested in the more theoretical parts of astronomy, and then more and more I started to actually think about mathematics and not so much about watching the stars through telescopes. And then I became a mathematician. Well, yeah, of course, that's a trickiest question. So I think we are in a very, very good moment for mathematics now in a few ways. One is that a lot of extremely significant problems have been solved. For instance, I never believed that in my lifetime I'll see the Fermat big theorem done and the Poincaré conjecture done, and they were solved. And also another thing that's very remarkable is that there are a lot of research mathematicians that are sort of geographically distributed. There are not just a few institutions that support research, there are many. And so in this sense, it's a very good moment. And then there are some challenges for the future, I think. And one comes from the way that the mathematics is taught, and it's this tendency to do courses by the internet and to distribute courses at distance, and this will change probably the way we do some things. And then another challenge is that we have to present mathematics to the public and to the funding agencies and to our external, to the society in general, in a way that remains appealing and to support the fact that, you know, applied mathematics is very important, but it cannot exist without a very strong support of fundamental mathematics. And so this is an important thing. It's funny that I was reading a book recently about mathematics during Kepler's time, and during that time mathematics consisted of arithmetic, geometry, astronomy, and music. And obviously, if you wanted to have somebody doing applied mathematics, you had to have him do pure mathematics because there was the same person. Nobody would distinguish between these two sides at that time. And it was already important to do mathematics. So all sorts of countries and leaders of different countries, kings and nobles, were essentially hiring mathematicians. And so today also we have to sort of defend the fact that mathematics is, it's in a good moment, it's progressing very well, and society has to be, this has to be reflected in our interaction with society. Then there's a third challenge, which is that our things become very, very technical, and we have to find a way to be still able to form graduate students in, kind of normal amounts of time, and for them to progress well, even if our subject is technical. And so, okay, but okay, I have good hope. It's not, but there are questions and problems that have to be solved. So that's it.